Yeah, Rahul, you can go ahead.
Thanks, Winky. My slides are visible?
Yes, can you put in slideshow mode? Presentation mode?
Yep.
Yeah, great. You can proceed, Rahul.
Okay, thanks. All right. Today I'm going to talk about running machine learning on really teeny tiny devices. So, what is the motivation? Basically, IoT is everywhere. Everything is becoming smart. We have a smart toothbrush. We have a smart fork. Anything and everything which is there, people want to make it smart by putting some ML on it. And the way the current smartness is achieved has a fundamental limitation. So what happens is that in these devices you have these sensors and there's a microcontroller which interfaces with these sensors. And in this talk we will be interested in small microcontrollers like milliwatt scale microcontrollers. And what this microcontroller does is it only collects data from sensors, sends it to the cloud. Some machine learning magic happens in the cloud, and then some response is received, and then the microcontroller acts in a certain way. Now, this architecture has three fundamental problems. One is that you have some latency of this network communication. Second, this network communication drains your battery. And third, you are moving collected data to the cloud, which has its own set of privacy issues. So, what we thought is that, well, we can solve this problem by just running machine learning inference on the device itself, right? So, no cloud, none of these issues will come about. And if we can do that, then we can actually do some cool applications. So FarmBeats is a project in our lab in which sensors are deployed on remote farms with no internet connectivity. And there is some ML happening on the microcontroller to judge whether the sensor has malfunctioned or not, right? So here, there is no internet connectivity. And so you want to run ML on the device itself to detect whether the soil or moisture sensor are working properly or not. Gesture pod is another application in which blind people use white canes and they can attach a device on the white cane, and then the machine learning running on the device can identify some gestures. So maybe the person does a double tap, and then the machine learning device identifies this gesture and reads out, for example, the current time. Right, and now you don't want to drain the battery, and you don't want to send all gestures which a person is doing to the cloud, right? And so here again, it will be great if we can run ML directly on the device. Now, the main problem of running machine learning on the device is that these microcontrollers, since they are milliwatt scale, they have very limited resources. So here is an Arduino Uno, a very commonly used microcontrollers. It has a read-only memory or a flash memory of 32 kilobytes, and it has a mutable memory, just 2 kilobytes, and it has no floating point units, right? And when we think of real-world machine learning algorithms, they are very hungry for resources. They are like megabytes or gigabytes of memory, and most of them use floating point. So in our lab, we have made significant advances in ML in which we have created machine learning models which can which need only thousands of parameters instead of millions or billions of parameters and still give good accuracy. And these are variants of decision trees or nearest neighbors or RNNs. And these machine learning algorithms have been specifically designed to be run on IoT devices. So here is the situation. We have a board like Arduino Uno, draconian memory and compute constraints, and then machine learning people have created these models that require very few parameters, like thousands of parameters. But even if we take these models, they will not run on this device because even though these models use thousands of parameters, since they are all floating point, which means 32 bits per parameter, memory still overflows, and all of these models are using floating point and there are no floating point units. And moreover, things which you are used to, like operating system, virtual memory, all of those things which help you run software, or everything is absent, right? So this is the situation today. If I want to run machine learning on CPUs or GPUs, I have many choices of frameworks available with me, and all of these frameworks use some kind of interpreter. When it comes to IoT devices, then they don't even have the resources to run an interpreter. And today there is a big gap between machine learning and IoT devices. And CDOT is our compilation based approach to bridge this gap. So CDOT takes a input model written in a DSL, and it takes the device constraints like how much memory you have, and it outputs some C code which is using all integer arithmetic, which can directly be run on the bare metal microcontroller. So to make C dot possible, we need to solve three problems, right? Absence of floating point units, low flash memory, and low RAM memory. So I'll deal with these problems one after another. So for floating point, uh, what we microcontrollers give you is integer arithmetic. So we can use fixed point representations, right? So floating point number like 3.23 can be represented by using an integer 25 using a scale of 3. And so this fixed point number will be in some error with the floating point number. And here the error is zero point 0.1 for a scale of 3. And this error depends on two things: the bit width, how many bits we are using to store the integer, and the scale, right? So how do we determine the scale? So suppose we use 8-bit integers and we vary the scale, then we get a graph like this. So as we are increasing the scale, the error is reducing, but at some point, integer overflow start happening and everything becomes garbage. Now, if we use 16-bit integers, then we can reduce the error even further. And here, basically, you can use a scale of 13 to get the best precision to represent 3.23 with 16-bit integers. And beyond scale 13, you start getting integer overflows. So what we can do is we can take machine learning models, run them on some inputs, see what the floating point values of the variables are, and set the best scale, which gives you the best precision while avoiding integer overflows, right? So we have solved the scale problem. Now, what about bit widths? Now, one solution is that just give 16 bits to all variables of the program. But if we do that, then the model will not fit on flash. We can give all variables 8 bits, and then the model does fit on flash, but accuracy tanks. And in some cases, accuracy just becomes equivalent to a random classifier. Now, if you have heard the hype about like 1-bit models or 2-bit models which preserve accuracy, then this might look strange to you. But what is happening here is that it is well known that if you have very few number of parameters, then you need higher bit widths. And so since our number of parameters are so small, even if we use 8-bit everywhere, our accuracy still tanks. And the solution which CDOT employs is to use heterogeneous bit widths, in which some variables are assigned 16 bits and other variables are assigned 8 bits. Now, if we have n variables in the program, then we have two choices for every variable, 16 bits, 8 bits. And so naturally, we have a 2 to the power n choices. And now we want to determine the minimal number of variables, which we keep in 16 bits, while still maintaining the accuracy of the execution. And here, we don't do the exponential exploration, we use a heuristic, which I'm going to show you next. So suppose we have 4 variables, A, B, C, D, right? And we keep all the variables in 16 bits and we get a accuracy of 97%. And this model doesn't fit within Flash. Now we decide that, okay, we are happy with 90% accuracy. So what can we do? Can we reduce some variables to 8 bits so that we are able to fit in Flash? So the heuristic we use is that we unsoundly assume that every variable affects accuracy in isolation, basically is independent of other variables. So we move A to 8 bits and keep the rest of the variables in 16 bits, run it and measure the accuracy. And we do the same for every variable one at a time. So this gives an estimate of how the accuracy is affected by a variable, right? And so here we see that, look, the variable A affects accuracy the least. So what we next do is that we demote variables cumulatively and measure the accuracy again. So we demote A because it was affecting the accuracy the least. Then we demote A and D because D was affecting the accuracy not as much as A, and it was better than other variables, and we do the same thing. And then we get this table. And then we wanted an accuracy of 90%, so we can choose this row. and then keep A, D, B in 8 bits and C in 16 bits. So the third problem, uh, which we have now, we have set the scale, we have set the bit widths. There's still the issue of RAM, right? So here on left side, I have a program, and on right side, I am showing the device memory, which is 3 kilobytes. So this red line shows the RAM limit. If we allocate a variable and it goes beyond the red line, then we have overflowed the RAM and the program will not run on the device. So let's see what compilers do today. They do what is known as static allocation. And if you do that, then we are going to overflow the RAM. And now you might be thinking that, well, we can do dynamic allocation. But I will tell you that dynamic memory allocation also fails. So in dynamic memory allocation, you allocate memory just before variable's first use, and you deallocate it after its last use, right? So here, this brown line shows the current execution state of the program, and then we start running the program. So we allocate A, we allocate B, we allocate C, and deallocate A, and then we deallocate B and we allocate D, and then we overflow the RAM. So what has happened here? So suppose we back up and we were here. Then if we had the foresight that a big variable D is going to come into the future, then we'll allocate C here so that when B goes away, D can nicely fit, right? So dynamic memory allocation runs into this problem of memory fragmentation, which is because the runtime is trying to minimize the runtime overhead of dynamic memory allocation. It uses very simple heuristics, which lead to memory fragmentation, which lead to memory overflows. But in C dot, the compiler knows the sizes of variables and their live ranges all at compile time because we are dealing with a DSL. And then C dot, what it can do is it can simulate the dynamic memory allocation at compile time so that there is zero overhead of memory allocation. So it computes a variable to address mapping at compile time so that all variables can fit in memory. And this is a bin packing problem, right? It's an NP complete problem. But since we are doing this memory allocation at compile time, we can throw heavy machinery at this problem. In particular, we use Canu's algorithm X, which is an exponential time algorithm, but it returns within minutes for our benchmarks with an optimal memory allocation schedule. In the worst case, C dot can even inject defragmentation code to pack variables together, but this hasn't really been needed for our benchmarks. So on that note, let me move on to some evaluation. So here on the x-axis, I'm showing the flash memory. On the y-axis, I am showing the accuracy drop. So if we consider the Uno device, then it has 32 kilobyte of flash, right? So if you overflow the flash, then you're not going to run on the device. Similarly, if your accuracy drop is high, then the deployment is useless. So there's actually a very thin green region in which feasible deployments lie. And now suppose we use 16-bit code, then the situation is something like this. And I'm not showing the floating point code because its flash consumption is out of this chart. So for some variables, we are in this green region and our accuracy drop is really, really low. But for some models, they will just fail to run because they overflow the flash. If we use 8 bits, then we don't overflow the flash, but our accuracy drop is very, very high. And with this heterogeneous bit widths, we just uh, fit in the green region, right? We get the accuracy similar to 16-bit code, and we get the memory consumption or the flash consumption similar to 8-bit code. Then next, the beauty of having a compiler is that we can generate code for other devices as well. So here are some results on FPGAs. So we took a Xilinx RT board, which is a tiny FPGA whose power consumption is similar to Uno, and we ran C dot generated code on this FPGA. So here we are using two machine learning algorithms, Bonsai and Proton, and the y-axis has latency in log scale. So we can run on a microcontroller, which is the Uno, and we get this blue bar about the latency. And then instead of running on the microcontroller, we can take the C code and use existing tools given by Xilinx to convert C to Verilog and run it on an FPGA. And just by making this switch, we get like a 1 order of magnitude improvement. Furthermore, instead of using Xilinx generated Verilog, If we use C dot generated Verilog, then we get another order of magnitude improvement. So just by switching from a microcontroller to FPGA, C dot can give you sometimes something like 300x improvement. Finally, we are right now building a POC for a battery powered IoT device which can take pictures of a room and determine how many people are there in the room. And here we are using a fancy RNN pool operator, which gives state of the art accuracies for the face detection problem. And this model uses something like 150K parameters. Now, this model is big enough that it cannot fit on the devices which I showed on the previous two slides. And therefore, we use this ARM Cortex M4 class device, which has 256 kilobyte of RAM and 512 kilobytes of flash. Now, if we were to use the usual compilation route, which is just takes floating point C code and compile it with the IDEs, then the models fail to run on this device. But by using C dot, we get something like a 32x reduction in RAM, and we get a 3.3x reduction in flash, which helps fit the model on this device. And I have a small 1 minute video about a preliminary evaluation of this device. And I think some people face problems with this video. I think half people hear this video, half don't. So, but I hope this will play fine this time.
Let's get started with the demo. Here we have an OmniVision 7670 camera module attached to an STM board housing an ARM Cortex M4 processor holding 192 KBs of RAM and 2 MBs of flash. We have already flashed our model onto this device and set up this blue button at the bottom to act as the camera trigger. We now click this button, which takes the picture and processes it. You should see a blue light currently lit up the board. Due to the demo constraints, we have already taken the picture that is now being processed here. When the green light hits back, the model processing completion is signaled, and we now have the results, which we will showcase on the computer screen. So here is the original image in which me and my sister are trying to hide each other's faces with our hands. And here is the corresponding result on the same image. To recap, we can take an image and run inference end to end on this cheap microcontroller, and it takes about 8.4 seconds per inference. Thank you.
All right. So this was all what we had done till now, and where are we heading next? So so I'm sort of a performance nut, and I try to get every ounce of performance out, right? And so currently what bugs me is that C dot uses these fixed point representations, which all hardware platforms support because everyone supports integer arithmetic. So we can run on arbitrary platform, but no one said that fixed point representations are the best representations. And recently there is a wave of new number representations. POSIX, Google created bfloat 16, NVIDIA created TensorFloat 32, and so on, right? And so my goal is the following: that someone gives you an ML model, gives you an energy budget, suppose 2 milliwatts, and says, run this ML model with the best accuracy possible in this energy budget. So what I want to do is that C dot should automatically select what are the number representations which are best suited for that model. And then we take an FPGA, which meets the energy budget, and then we burn hardware for doing this arithmetic over these number representations and the memory devices all on the FPGAs, so that we get the best accuracy or the best possible implementation of the model, which meets the energy budget. All right, so to conclude, C dot is a compiler which takes a high-level DSL uh, input, which describes the ML algorithm. It takes input the constraints of the device, and it generates code which can actually run on the device. And C dot is the first unified framework which generates code for both microcontrollers and FPGAs. Using C dot, we have been able to run RNNs, and this is the first evaluation of its kind of running RNNs on an Arduino Uno, a device with just 2 kilobytes of RAM. And then I've also shown you a demonstration of phase detection on an ARM Cortex M4 class device. So to conclude, hopefully I've convinced you that C dot bridges the gap between machine learning and IoT devices. And if you want to learn more about C dot, then we have some papers. So the PLDI 19 paper describes the floating point to fixed point conversion. And there we outperformed the float to fixed converter of MATLAB by something like 50x. The UFLA paper describes in detail our flash and RAM management mechanisms to reduce memory. And the FPL paper describes the FPGA results. We have also released a Medium blog post which describes the step-by-step process for running this phase detection on the microcontroller of your choice. So that's it. I will be happy to take any questions. Thank you.
Yeah, thanks, Rahul, for a very nice talk. Anyone has questions? Srijit has a question. Yes, Srijit, go ahead.
Hi, hi Rahul. Sorry, my understanding of like computer architecture is very limited, so my question might appear naive. Uh, so you are saying that you want these things to work in IoT device, etc. So my question is that uh, within time, won't all IoT devices also start having more RAM and like won't such a scenario happen and then we can start running standard algorithms there, or this is not something which might happen and your algorithms would be preferred? What was your take on that?
Yes, so that is a very good point, right? So what is happening is that hardware devices are becoming more and more powerful. But what is also happening is that the machine learning models are increasing in complexity or size faster than what the devices are doing. So what happens is that machine learning people say that, well, you give us some memory, right, and we'll occupy all that memory to get the best accuracy as possible. So this problem of fitting large ML models on the device, this remains, right? Instead of 2 kilobyte, it becomes 200 kilobyte. But the problem, which is to fit a big ML model on a small memory, that problem remains the same because the ML models also keep becoming more powerful.
Yeah, and another point, Srijit, is that usually the cost is involved in increasing the size, capacity of the memory, and vendors don't want to increase costs because they lose consumers. So even if you look at cars, although machine capacities have increased, they haven't really moved to high-end machines, even in cars. So they'll continue to use very devices, low capacity devices.
Thank you. I think I understand the main motivation. Thanks.
Anyone else has any questions? Yeah, Supratik.
Yeah, thanks, Rahul. Wonderful talk. Uh, this is perhaps not quite related to what you spoke about, but certainly, in the general area. So, given that, there is need for putting these sophisticated machine learning algorithms on edge devices, uh, would it make sense to sort of come up with new, maybe networks which are not very deep, networks which do not use billions of parameters? I mean, what I'm saying is, can I mean, can machine learning models custom made for such edge devices also be designed? Uh, I mean, I know this is orthogonal to, I mean, what you're doing is you're taking an existing machine learning model and you're trying to make it fit on the edge device, which is great. But if these applications on edge devices are going to become important, as they are, as I believe they will, uh, I mean, shouldn't it also be necessary to think of, I think, things like what bonsai does in a certain sense. I mean, it's still not, I think, targeted for very such low resource devices, but it comes up with classifications which are very short trees and all of that, right? Low
Yeah,
res- So
yeah, you're absolutely right, right? So if we have a model which has millions or billions of parameters, like there's no way it's going to run on an Uno. So we need improvements on both fronts. One is that we improve our machine learning so that models go to thousands of parameters and still maintain accuracy, right? So that is the research like bonsai, right? And but machine learning people, I think they are all training or are more familiar with floating point arithmetic, right? and when they create these models, they always assume that there is plentiful of memory, right? And so there is one direction of like compressing these machine learning models to be as small as possible. But then the problem is that even if you get that model, going to a device means solving systems level challenges, right? Which is what uh, I talked about, right? Like
Yeah, yeah,
no
exactly.
OS, no virtual memory, so you get fragmentation, right? So machine learning people are not going to solve the fragmentation problem. That comes to us PL folks. So this what you are saying is absolutely right, right? That we need both. It cannot be done like only ML people cannot solve it, only we cannot solve it. We need the ML people to create some models for which there is some hope of putting them on device, and then we can take it from there.
Yeah, yeah, great. Yeah, I think that's what I think. Machine learning folks should be systems aware, and we need to be machine learning aware. And but this is great work. Yeah, it bridges that gap.
Yeah, thanks.
Yeah, Rahul, I have a couple of questions. One is in the demo that you showed of recognizing faces.
Yeah.
How did you optimize the machine learning model? Did you train a separate model, build a different model, or did you optimize an existing model for size?
Yeah, so there was this RNN pool model which was published in Eurex 2020. We took that model, right? And what we do is you can say something that called post training, right? So someone gives us a train model, and what we do is then we do this quantization, move from floating point to 16-bit, 8-bit integers, allocate RAM cleverly so that it runs on that device. Right? So
So, okay, so those are the only modifications you did to that model that was
yeah.
available. Yeah, okay. And the second question is, does your compiler also reorganize code so you can, based on data dependency, etc., you can restructure your code so that memory consumption can be. I can imagine one would be able to do that. Maybe that will simplify your memory allocation problem.
Yeah, so we haven't done that. That is a good point that we don't move around the program statement execution order, even though since our compiler is dealing with a DSL, it has all the data dependency and it has all the information to do that. But we haven't done that till now. And yes, I think if we do that, then our RAM consumption can go even lower.
Yeah. Thanks. If there's no more, there are no further questions. Yeah. Thanks to the speaker. Good talk.